Testing, 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 testing. We'll be starting in just a moment. Welcome, welcome. We will be starting as soon as we'll be starting as soon as we get a few people in here. Howdy, howdy. And if you're watching from YouTube, which you can do now, make sure to pop on over and, you know, check that out. This will be streaming straight to YouTube. Meaning, oh, did I screw up the numbering? I think I screwed up the numbering. Yeah, that's okay. We can fix this. We'll be starting in a minute once we get a few more people in here. Don't worry. Thank you for the galaxy, Dr. Roger. Or Daddy Roger. Dr. Roger. Thank you. Thank you. Welcome, welcome. We're going to be starting in... Oh, where'd it go? There it is. We'll be starting in just a moment. Today's paper that we're going to be reviewing, by the way, is called Cosmological Constant as an Integration Constant. Now, I guess we'll see if this is actually like a good paper. I don't pre-read, but it probably is. It's hard to... Come on. There we go, better lighting. There we go. Hopefully the text isn't so small that you can't read it. Don't worry, you'll be fine. You will be fine. It's okay, Roger. No, nobody thinks flat Earth is real. All right, we should get started. So, today's paper is about the cosmological constant. It's written by Justin Feng and Pisin Chen. The paper is called Cosmological Constant as an Integration Constant. It was first published about 6 months ago, but it's since been updated as of yesterday. So why don't we get started? So let's just read the abstract. It's a good place to start. And I'll explain as we go. If you're new here, if you haven't seen these kinds of review live streams, then this is the thing that I do once a week. So sit back and enjoy. We're going to talk about some frontier science, right? So, let's get started. So, the discrepancy between the observed value of the cosmological constant and its expected value from quantum field theoretical considerations motivates the search for a theory in which the cosmological constant is decoupled from vacuum energy. So let me back up, explain what the cosmological constant is. The cosmological constant is what's believed to be driving the accelerated expansion of our universe. Now the trouble is that it's a very, very small number. Like if you measure it in the right units, it's very, very small. And if you think that the cosmological constant is caused by kind of these quantum fluctuations of the vacuum, which that's a potential cause of the cosmological constant, then you're off by like 60 orders of magnitude. So that's not good, which means that if the cosmological constant is really what we think it is, then it's probably not caused by that. So they're saying that they want a search for a theory in which the cosmological constant is decoupled from the vacuum energy. So they're going to try to come up with some alternative explanation for this thing. In this article, we consider the viability of theories in which the Einstein equations are recovered without additional constraints. The Einstein equations are just our standard theories of, it's just our standard theory of gravity that Einstein came up with, and in which this cosmological constant is regarded as an integration constant. You guys remember when you would do an integral and then you would add the plus c? That's what they're going to try to get. These theories include trace-free Einstein gravity, theories constructed from the Codazzi equation, which includes Cotton gravity and a gauge gravity-inspired theory, and conformal killing gravity. Killing, by the way, is the name of a person. It's an unfortunate name, but it was a guy's name. It has nothing to do with unaliving or anything. We remark on a recent debate regarding Cotton gravity. If you've been following me on TikTok for a while, you would remember that there was drama regarding Cotton gravity at the beginning of last year. So this is what they're referring to. And find that while the Codazzi equation of that theory is indeed underdetermined, the solutions of the Codazzi equation trivialize to lambda g on generic backgrounds. So I'll explain what this is later when we get into the meat and potatoes. And that in principle, one can close the system with a divergence-free condition and an appropriate choice of initial data. We also propose a full variational principle, full in the sense that variations in all variables are considered, for each of the aforementioned theories that can incorporate the matter sector. So they're going to basically give a nice theoretical justification for each of these theories that will generate what they want it to generate. In this matter, we can obtain the trace-free Einstein equations without a unimodular constraint. I don't know what a unimodular constraint is, but we'll read and we'll be able to figure it out. Don't worry, we'll make it bigger in a minute. I'm just reading out loud. The resulting actions require additional auxiliary fields and are therefore only expected to be effective, but they may provide a useful starting point in bottom-up approaches to constructing more fundamental theories. All right, let's zoom in and read the paper. Hopefully this will be the right size. Let's just center that. Looks good. Just double checking that we're good in all regards. Oops. All right. So let's read an introduction. Since Einstein, oh, by the way, if you're wondering, this is being streamed on YouTube right now, and the live stream will be available on YouTube after the live ends. So if you miss it, you can always go back and rewatch, which I would highly recommend. Since Einstein introduced the cosmological constant to his equations in 1917, the debate about its nature has never stopped. Before the discovery of the accelerating expansion of the universe in 1999, that won the Nobel Prize, by the way, in 2012, maybe? The main consideration was whether the cosmological constant is exactly zero. See, for example, the famous review by Weinberg. Oh, that's the end of the sentence. The main consideration was whether the CC is exactly zero. In the aftermath of the discovery of the accelerating expansion of the universe, the problem became more acute. The notion of dark energy introduced to account for this effect behaves like the cosmological constant. Indeed, in most analyses in cosmology, such as that of the cosmic microwave background, the cosmological constant is commonly invoked in the modeling. So our best models of the universe all rely on a cosmological constant being in the equations. If true, then the observed value for the cosmological constant, fixed by observations of the accelerating expansion of the universe, is many orders, up to 120, I believe it's actually down to about 60, many orders of magnitude smaller than contributions from vacuum fluctuations arising from quantum field theoretic considerations. The discrepancy between the vacuum energy and the observed value for the CC requires an extreme amount of fine-tuning. This is what's known as the fine-tuning problem. On the other hand, the Einstein field equations have been well established on astrophysical scales, even in the strong gravity regime. This state of affairs strongly motivates a modification or reconstruction of Einstein gravity. So what they're saying is, look, we have this fine-tuning problem if you assume that Einstein gravity is correct. But what if we slightly modify Einstein gravity? Will we still have the fine-tuning problem? That's the goal of this paper. In this article, we consider one strategy, discussed in section 7 of 58, in which one seeks a formulation of Einstein gravity in which the CC arises as a constant of integration in a matter independent of vacuum fluctuations, avoiding the need for fine-tuning in this regard. Though the most well-known of these approaches is that of unimodular gravity, which I'm not familiar with, but they provide a whole bunch of references that we could look at if we needed to, which can be formulated at the level of the action, unimodular gravity introduces a constraint on the metric determinant that breaks general covariance. So I should be specific here. General covariance is this idea that, like, regardless of the coordinates that you choose, you can always, the physical quantities don't care. So breaking general covariance is generally a bad thing. We really like general covariance when we're talking about spacetime, because it shouldn't matter how you describe spacetime, it should give you the same physical quantities. On the other hand, at the level of the field equations, there are several proposals in the literature that do not require such a constraint. Our main aim in this article will be to evaluate the viability of these approaches. Cool. A proposal originating from Einstein is that of the trace-free Einstein equations, which are recovered in unimodular gravity but can be considered on their own without the unimodular constraint. That's fine. Let me pop something out really quick. There we go. Oop, there it is. Another proposal by Cook and Chen, inspired by a set of third-order equations developed by Kilmister, Newman, and later by Yang, is to construct a gravity theory from the Bianchi identities and derivatives of the energy-momentum tensor. I'll explain what all of these are. Thank you for the level-up sparks. I'll explain what all of these are when we get to them, but this is just a bunch of different ways that they can develop new theories of gravity that, in some sense, reduce the original Einstein gravity. We focus primarily on the aforementioned approaches, though we mention here other proposals in which one may obtain the unconstrained Einstein field equations with the CC arising as an integration constant, such as the thermodynamical approach of Padmanabhan, a modified metric affine theory, and contributions from a three-form action. More recently, and this is where the drama was. More recently, Harada proposed two theories of gravity. Can I center it a little? Yes, I can. Let me center it just a little. How's that? Is that better? Something like that? Yeah, it's probably good. More recently, Harada proposed two theories of gravity termed Cotton gravity and the so-called Conformal Killing gravity. Cotton gravity is constructed from the Cotton tensor, or as someone who I won't name called it, the Coton tensor, which is, I guess, technically correct. And it has been shown that one can rewrite the field equations of Cotton gravity as a Codazzi equation. So I need to explain what Cotton gravity is, and I will go into more detail in a bit, but one of the ways that I should explain what the Cotton tensor is. One of the ways that we describe the curvature of spacetime is through quantities called tensors. Now you can think of these as like multi-dimensional matrices. So a two-dimensional matrix would be like, a square grid of numbers. A three-dimensional matrix would be like a cube of numbers. A four-dimensional matrix would be like a four-dimensional hypercube of numbers, and so on. So it's basically just, for those of you who are involved in like computer science, it's like a multi-dimensional array. It has the special property, however, that multi-dimensional array, like the actual values in the array, change in a very precise way when you change the coordinates describing that array, because each direction, or each value represents a coordinate component, and those coordinates can change, right? You could work in polar coordinates, you can work in Cartesian coordinates, whatever. Anyway, so the way that we describe curvature in spacetime is with something called a Riemann tensor. And one of the ways that you can kind of extract information from that Riemann tensor is kind of by throwing out some information and averaging over some of the pieces. So you start with a four-dimensional array and you end with a two-dimensional array, kind of by throwing out two dimensions. That's what it's called the Ricci tensor. The Cotton tensor is, in some sense, a derivative of the Ricci tensor. You could also phrase it another way so that it's a derivative of the Riemann tensor. It's just a different way of differentiating it. So in some sense, it has one more derivative than the Riemann tensor does. The Riemann tensor takes two derivatives of like space-time, and the Cotton tensor takes three. So when we talk about Cotton gravity, what we're really talking about is we're talking about a set of equations that depend on the Cotton tensor rather than on the Ricci tensor. So it has one more derivative than the normal Einstein equations have. So let's continue where we were. Cotton gravity is constructed from the Cotton tensor, and it has been shown that one can rewrite the field blah 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 equations of Cotton gravity as a Codazzi equation. So this is just another way of writing the equation for Cotton gravity. So C here is the Cotton tensor, and then this upside down triangle thing, that's a derivative. In this regard, Cotton gravity is in the same class as the earlier theory of Cook and Chen, as we will show that the field equations for the latter can also be reformulated as a Codazzi equation. Conformal killing gravity has a different structure altogether, as the field equation resembles the defining equation for a conformal killing tensor. There's also formulas for that, and I'll explain that in a bit. By the way, if you're just joining us, the paper that we're discussing today, that we're reading, is called Cosmological Constant as an Integration Constant. This video is being streamed on YouTube. You will be able to rewatch from the beginning if you'd like to, at the end of the stream. This is not a Cotton gravity update, actually. This is just it's a review that involves Cotton gravity. Let's just put it that way. Right, so Cotton gravity was recently the focus of a debate. It's true, I went over it on TikTok, over its viability as a physical theory, as it was discovered that the symmetry-reduced equations of Cotton gravity are underdetermined. Roughly, this means that from the equations, you can't uniquely determine what space-time looks like. There's just not enough information in the equations. It has been argued that while the equations of Cotton gravity are indeed underdetermined in cases of high symmetry, for instance, cosmological or spherically symmetric spacetimes, this is not necessarily the case in generic spacetimes. So right now, they're just going over the drama, right? This is history. Similar concerns apply to the theory of Cook and Chen, as they share the same Codazzi structure. Another concern that applies to Codazzi-type theories and conformal killing gravity is the fact that they are only defined at the level of field equations. It's kind of a problem. These theories suffer from the lack of a complete variational principle, as the variational principles proposed so far require holding some of the variables, such as the spacetime metric, fixed. I'll finish this paragraph and then I'll explain. One difficulty is that the energy momentum tensor is obtained from variations of the metric tensor in the matter sector, but derivatives of the energy momentum tensor appear in the field equations. So let me explain. So just as a clarification, Cotton gravity is just a more complicated version of Einstein's gravity that has more stuff going on in it. It's a different theory of gravity, but it's closely related to Einstein's gravity. So it's just the name of a theory. Now I just want to double check something. Right. So this whole business, this is the problem that they brought up, is that Cotton gravity and Codazzi type theories, they don't have a variational principle. And a variational principle is roughly this idea that there is some quantity that the solutions of the theory, in this case, the spacetimes that satisfy Cotton gravity, there is some quantity that those solutions make that quantity either maximum or minimum, extreme in some sense, when you vary all of the possible parameters. The trouble is Cotton gravity doesn't have that. Neither do Codazzi type equations, just because it's they're a sick theory in some sense, but it perhaps isn't entirely fatal. Anyway, let's keep reading. As remarked earlier, the primary aim of this article is to assess the viability of the aforementioned approaches to decoupling the CC from the vacuum energy, without introducing additional constraints. We focus on two specific requirements. First, we require that the field equations can be reformulated in a manner that yields a well post-initial value problem. A well post-initial value problem is just this idea that you start with the initial data and it will tell you what happens in the spacetime afterwards. In doing so, we aim to shed light on the recent debate over the Codazzi equation. Okay. Second, we propose variational principles, including matter, for the trace-free Einstein equations, the Codazzi equation, and the conformal killing equation without introducing additional constraints. This is a really cool thing that they're going to do. Presumably, they're going to give some nice variational principles. That's good. It should be noted that some variational principles for the trace-free Einstein equations were recently proposed that avoid additional constraints, but our approach is the only one so far to explicitly incorporate the matter sector while avoiding the need for fine-tuning. When they say the matter sector, typically want to vary all possible things, and that includes the matter. And so you have to make sure that that's included. Though our proposed actions are not intended to be fundamental, as they require the introduction of auxiliary fields and ghosts, which do not exhibit classical pathologies, they may serve as a first step towards a more complete theory. They're going to introduce ghosts. That's bad. That's real bad. What the fine-tuning here is referring to the fact that the cosmological constant seems to be very, very small compared to what it should be. So, they're going to tell us about their theories. The theories we consider here differ significantly in their construction, but they all share the property that they yield the unconstrained Einstein equations in a matter that is entirely independent of the vacuum energy contribution in the energy momentum tensor. The energy momentum tensor is just the quantity that describes the matter and the energy that's present. This avoids the need for fine-tuning, with the cosmological constant arising as a constant of integration. So it's just a fitting parameter rather than something that comes from the physics, which means that while it's less predictive, it does mean that you don't have to have fine-tuning. Ghosts are bad because they seem very unphysical to me, and they agree. In this section, we briefly review the aforementioned theories. So now they're going to go over the theories that they're going to discuss, which will be great. All right, let us jump in. I'm going to have a lot of explanation to do, but we'll do our best. The trace-free Einstein equations may be obtained by assuming that the determinant of the metric, I should specify what that means. The metric tells you how big distances and times are in spacetime. The determinant of the metric basically tells you how big a volume of spacetime is. Right, it may be obtained by assuming that the determinant of the metric is held fixed under the variation of the action. So you vary the action. This is that quantity that you want to minimize or maximize. But this time you're not going to vary, you're not also going to vary the size of spacetime. You're just going to vary the thing that you are adding up everywhere in spacetime. In this form, the theory is called unimodular gravity. However, the equations themselves can be written without assuming such a constraint. So here they're just telling us what the equations are for this theory. So this, I'm going to start with the one on the right. The theory, this equation on the right, so remember that T is the stress energy tensor. It tells you where the matter is. Yeah, well, so Ethan, the point is that they just do it. Like, you're not varying the whole action in an arbitrary way. You're not doing an arbitrary variation. You're just doing it. Anyway, so T is the stress energy tensor. It tells you how much stuff there is, where it is, how much energy it has, how fast it's moving, all of this stuff. And so this symbol here is just a statement of energy conservation. It says that basically the amount of energy that you have here stays the same, except for the stuff that enters and leaves, and then the same is true for momentum and stress and pressure. Essentially, this is a statement of conservation. This is the actual dynamical equations that tell you how space-time is related to the matter. So here we have the Ricci tensor. I brought up what the Ricci tensor was last time. Roughly speaking, the Ricci tensor tells you how... there's a good analogy for this, and I can't remember it. The Ricci tensor basically tells you if you have a cone shooting off in some direction, it tells you how the area of the circle produced by that cone differs from how it would in Euclidean space. So this is some sort of measure of curvature. So that's what the Ricci tensor is. And then you're subtracting off a certain amount of the Ricci scalar. Now the Ricci scalar tells you how big a sphere is related to its, or how much volume a sphere has in relation to its radius. Again, in a non-Euclidean way. So the Ricci scalar should be 0 if it's Euclidean. If it's non-Euclidean, then this volume of the sphere might not be directly related to its radius. Anyway, so what we're doing is we're taking the difference of these two things. This G here, that's the metric tensor. It just tells you how long distances and durations are in spacetime. So this left-hand side, that's the curvature of spacetime, right? It's a way of capturing the curvature. And then they just say it's equal to this particular combination of the matter. So the typical Einstein equation has something slightly different on the left, and then it only has this t term on the right. They're just making a correction so that if you were to, the 1/4 is just the trace. So this is just a trace-free combination of the Ricci tensor. So essentially, if you were to add up along the diagonals of this tensor, or of this matrix, because this is the 2x2 matrix, you would get you would get a total of 0 along the diagonal, and so they're doing the same thing over here. Yeah, trace-free just means that if you add up the numbers along the diagonal of the matrix, you get 0. That's all. So, this is in contrast with the regular Einstein field equations, which are not trace-free, so if you add up along the diagonal, you don't get 0. It's just a slight modification. I'm not going to finish the update for Chrome, no. I refuse. Oh, let me center this slightly better. How's that? No, this is 1/4, not 1/2. This is not the Einstein field equations. These are the trace-free Einstein equations, not the Einstein field equations. So if you're wondering why it's 1/4 and not 1/2, That's why this is not the Einstein field equations. That 1/4 basically comes from the fact that there are 4 dimensions of space. So if you add up the diagonals of this metric, of this matrix, you get 4. Why are zero sum diagonals called trace-free? The trace of a matrix is just the sum along the diagonals. Yeah. Anyway, so here R with a little bar underneath it. Why is that bar there? I don't know why they put that bar there. This R is the Ricci tensor, as I said, and then T with these Greek indices, this is the conservation equation, is imposed as an independent condition on the energy momentum tensor. The contracted Bianchi identity, this is just a true fact about curvature. If you take the derivative in the right way of this particular combination of curvature terms, you get 0. Combined with this equation implies that the derivative of the scalar curvature plus the derivative of the trace of the stress energy. The trace of the stress energy is just, again, a combination. It's just the sum along the diagonals of that tensor. That gives you 0. And so because you can differentiate that, or because this is a very simple equation, it's a scalar equation, you can just write down a solution. The solution is that R plus KT is a constant. So if the derivative is 0, then the thing itself is a constant. So that means that the Ricci scalar plus the trace of the stress energy, which is, again, just a measure of mass and energy, is a constant. And here they're saying that this is the integration constant. This is lambda. Solving for T and plugging this back into equation 1 yields this. And so now we have something that looks a lot like the Einstein field equations. It's not, well, actually, it looks almost exactly like, actually, this is the Einstein field equations with cosmological constant now. So what they did is they took the trace-free Einstein equations, used the Bianchi identity, combined it with this equation here, of these equations, and then solved the differential equation. You wind up with the Einstein field equations, but now you don't. Now the cosmological constant is free. Yeah, it's this is the true Einstein field equations with a cosmological constant, but that came in as an integration constant. Sorry, I just have to mute somebody. Okay, so later we consider a variational principle that does not impose a unimodular constraint on the metric. Fine. All right, so that's trace-free Einstein equations. Very, very simple. You get these nice, you get this nice cosmological constant out for free. All right, let's look at Bianchi gravity. The works of these references consider a field theory in which the connection and curvature tensors are treated as analogs of the respective gauge field and field strength tensor of electrodynamics. I should explain what these words mean. So the connection basically tells you what happens if you take an arrow and you drag it along spacetime. What happens to that arrow? Does it get longer, shorter? Does it change direction? That's what the connection tells you. The curvature tensors are the things I already described. So here they're saying that the connection and the curvature tensors are the analogs of the gauge field. Think of this as like the so the gauge field is like the electric potential if you're doing electrodynamics, and the field strength tensor is like the electric field. So this is kind of doing gravity as an analog of electrodynamics. And so if you do that, then you can get this other field theory where you take a particular combination of derivatives of the Riemann curvature tensor. That's what this R is. See how it has 4 indices? It means it's a 4-dimensional matrix. Where does the trace-free field equation come from? Are they equivalent? No, the trace-free field equation just is a completely different set of field equations. Like it has more freedoms. It's just a different theory of gravity that somebody came up with a while ago. I guess in these references, but it reduces to the Einstein field equations with a cosmological constant. Right. So if you take a particular combination of derivatives of the Riemann tensor, this is called the Bianchi identity, you get 0. That's just a true fact about Riemann curvature tensors. That particular combination gives you 0. And then they also postulate one additional piece of information, namely that if you differentiate the Riemann curvature in another way, I'm not going to go into the details of what this means. Essentially, it's the divergence of the Riemann curvature tensor, if you remember from your vector calculus. And then they attach on some source, some something that tells you about how much matter there is. So the derivative of the Riemann curvature tensor tells you something about the matter. So that's what they're considering here. Here, equation 3 is the Bianchi identity, like I said. This guy is the curvature tensor, the Riemann curvature tensor, like I said. And then one postulates the source, this J guy, to be integrable, so that for some symmetric rank 2 tensor T, it may be written as this. So J is not just anything, it's not just anything, any type of matter. In particular, it is the derivative of some type of matter, of some matter thing, something that has to do with matter. The field equation 4 may therefore be rewritten, so you take equation 5, plug it into equation 4, and you end up with this guy. So here you're applying the traced version of the Bianchi identity. So you take the trace of this equation, you take the trace of this equation, use it to rewrite this term in equation 4, and you wind up with that term. Then you plug in equation 5 back into equation 4, and then you get this term. There's a lot of algebra happening there, maybe even a little bit of calculus, but it's suffice it to say it's not that bad. They're not doing anything sneaky here. And so here T bar is not the exact same as the T that we had up here. It's not the stress energy tensor, but it's like a slight modification of it. They call it a trace reversal of the energy momentum tensor. So rather than having the trace be the positive, basically they replace the trace of the stress energy tensor with the negative of the trace of the stress energy tensor. So basically they flip the sign along the diagonal. Yeah, roughly what they do. So this is another type of curvature, or this is another type of gravity equation. It tells you that the curvature, which is this term, is related to the matter, which is this term. That's what the Einstein field equations is. Yes, capital T without any indices is just the trace of the stress energy tensor. Right, so one class of solutions for equation 6 corresponds to the trace reversed Einstein equation up to some integration tensor. That's horrible. So essentially you can solve this equation, or rather you can check that this equation, if you plug in r equals this, that will be a solution to this equation 6. Is there a way that you can view this paper? Absolutely. Yeah, so the paper is called Cosmological Constant as an integration constant. It's available online for free. The archive number is 2406.00932v4. You can just type that into Google and you'll find it. Right. So this is one class of solutions. You can just plug it in, and then you'll find that it actually does equal 0 here. The k terms and the t terms will cancel out, and you'll have this extra x, which won't show up because you're taking an anti-symmetric piece. X has to satisfy certain constraints. So X has to be symmetric. So these subscript indices here, those are just like the labels for the components of your multidimensional array. So they can be anything from 1 to 4 because their space-time is 4-dimensional. So this is just saying that X, viewed as a matrix, X is symmetric. You can swap the indices and get the same thing. It's also saying that its divergence, again, in the sense of vector calculus, its divergence is 0. And it's saying that its curl is 0, again, in the sense of vector calculus. So it just has to have those properties. If it has those properties, then you can plug this into equation 6 and you get 0. So this is a solution to the Bianchi gravity equation. The tensor x mu nu is assumed to be determined by boundary and initial data. So it's just kind of like free data that you specify initially. If the initial boundary data yields x mu nu is proportional to the metric, remember g is the metric here, and lambda is just a number, then the cosmological constant little lambda may be interpreted as an integration constant. We discuss later how such solutions arise from initial data. So this is again how we can get the cosmological constant as an integration constant, which is what we want. One might imagine rewriting equation 6 as this guy. So you can just rewrite this thing as this, where k, it happens to be this particular combination. So all you're doing is you're kind of grouping terms and then combining things. You're plugging in what t bar is here, and then you're kind of expanding out and collecting. That's all you're doing. And then you get that it's the curl, like the genuine curl, of this particular tensor, and then that tensor has this form. So they say, and this is correct, why they call it a Codazzi type. So because we have the curl there, They say that equation 9 has the form of a Codazzi equation. A Codazzi equation is just a curl, which is of recent interest in the Cotton gravity program. The Cotton gravity program also has a Codazzi equation. Right. Let's keep reading. Okay, so that was Bianchi gravity. Bianchi, by the way, is spelled, it's an Italian name. Bianchi. No, I'm not moving to Red Note, at least I haven't yet. I'm going to be on YouTube. In fact, I'm on YouTube right now. Hi, YouTube. Everybody say hi to YouTube. Well, they can't see you, but what they can see is they can see this. Bianchi is not unimodular, no. Well, actually, it's not clear. They're probably going to derive a variational principle, and then it might turn out that it is, but I don't know yet. Anyway, so now let's talk about Cotton gravity. So Cotton gravity is based on the Cotton tensor. So like I said earlier, the Cotton tensor is just it's one type of derivative of the Ricci tensor. Now the Ricci tensor, again, it tells you how the surface area of a cone changes as you move out. How the size of the tip of the cone changes as in a particular direction. So if you take the derivative of that, then you get this thing called the Cotton tensor, and it's really hard to intuit what this thing actually means, what this geometric object means, but it has something to do with the curvature of spacetime, and it's just a particular combination of curvature tensors that happens to show up a lot. You do need to study tensor calculus before learning this, yeah, probably, or you can just pick up a general relativity course. All right, so then they just define a new tensor. So this is the Cotton tensor. It's a well-known thing. It's named after a guy whose name is Cotton. Not Carton, Cotton. By the way, y'all, if you're watching on TikTok, go subscribe on YouTube. Then you can see this more when TikTok goes away. It's better that way anyway. Then they define this new tensor, T ABC. It's a curly T. And this is just, again, it is a particular type of derivative of the matter tensor, the stress energy tensor. But notice that it actually has the same form, right? So we have BAC, BAC, CAB, CAB, and then it's like the same thing. They're just replacing an R with a T. And that's intentional. Then one can write the field equations for Cotton gravity as saying C is equal to T. The reason I'm moving to YouTube is because the majority of my audience is in the US. Why is T curly T? Because they're just defining a new thing. This is a new matrix or a new array. So they have this new equation. This is the Cotton tensor equation. It tells you something about the curvature on the left-hand side is equal to something about the matter on the right-hand side. This equation can also be rewritten. It can be written in terms of this kind of Codazzi form, where you have the curl of some tensor is equal to 0. And here, they're defining this curly C. This curly C is G, which is just a particular combination of Ricci tensors and Ricci scalars. Curly G minus T. And then there's some other stuff that you're adding in. This G is the trace of this G, T is the trace of this T, and then X is just the same X that we had before. It's just this X that we had before. So we're left with a Codazzi type equation. But again, it's just another equation relating space-time curvature to matter content. Fine. One moment, I'm just going to grab my water bottle. And I'm going to fill it up. All right, I'm back. So, then they have another gravity theory that they're going to be reviewing. Conformal Killing gravity. Again, named after a guy whose name is Killing, not just a funky name. It's the guy's name was Killing, which is unfortunate, but it is what it is. So, the equations for the so-called conformal killing gravity theory proposed in 27 may be written in this form. So again, they have a so here they have now they're using different notation. This is terrible. Do they actually explain the notation? I know what they mean. So here, what this means, so they have an array, a tensor called K, and it's a two-dimensional array because it has two indices. And then if you see a semicolon, that means you differentiate once. So you're differentiating this K once, and then you're differentiating this K once and this K once. And then you're setting that equal to, oh, this is even worse. Okay, this is a covariant differential, meaning that it's a coordinate independent way of differentiating, so it doesn't depend on what coordinates you pick. And then over here, oh, this is awful. This is so terrible. Here, oh no, actually that's a trace. And then they're setting that equal to the derivative of the trace of K. So you're differentiating, you're taking the trace of K, you're summing up along the diagonals, and then you're differentiating that. Let me make sure that this is nice and centered. No, let's zoom out once. Okay, there we go. So, the equations for the so-called conformal killing gravity is this. Now here they're defining what K is. So K is a combination of the matter tensor and the Einstein tensor. G is the Einstein tensor. It is just some combination of the Ricci tensor and its trace. So it's just another way of writing down the curvature of spacetime. Now, the equation above has the form of the equation for a conformal killing tensor. Now, I should explain what a conformal killing tensor is. A conformal killing tensor is just any tensor, doesn't have to be curvature, it's just any two-dimensional array that has certain certain nice properties, that if you essentially you want to, it's really hard to explain what's actually happening. These things are things that describe so-called hidden symmetries. And it's really hard to explain what those are intuitively. But suffice it to say, it is just any tensor that satisfies this equation. You differentiate your two-dimensional array and take a particular combination, and then that's equal to a thing that depends on the metric, the way that you measure distances and length, distances and durations, and then some other vector. This is a vector here. Technically it's a one form, but it's equivalent to a vector. So here they're telling us that UA is a one form. A one form, just think of it as, yeah, you can think of it as a vector. They're isomorphic on Riemannian manifolds, or pseudo-Riemannian manifolds anyway. And then K is a symmetric killing tensor when U is 0. So K is symmetric, meaning that if you swap the two indices, you get the same thing. So if you looked at the 1,4 component of the array, it would be the same as the 4,1 component. So this is just a particular type of thing. It's called a killing tensor because it satisfies the killing equation, which is named after somebody whose last name was Killing, which is going to get me banned on TikTok, but whatever. TikTok's going away anyway. Don't care. Right. So however, as pointed out in these references, a simple redefinition to get k bar equals 6k minus gk reveals that any non-trivial solution of 16, so if you try to solve this equation, which is a horrible equation, by the way, yeah, the unaliving tensor, there you go, requires the existence of a killing tensor given by k bar. So, so if you redefine, if you define k bar this way, then the solutions of 16 must have a killing tensor. It just has to. It follows that solutions of equation 16 either trivialize to k being a constant times the metric, or they admit a killing tensor. For this reason, it is perhaps more appropriate to refer to this theory as killing tensor gravity, but we retain here the common terminology in the literature. Moreover, we note that perturbations of killing tensor solutions satisfying k not equal to minus lambda g Must also admit a killing tensor since our universe, or must also admit a killing tensor. Since our universe, being inhomogeneous and anisotropic on small scales, does not have the required symmetries to admit a global killing tensor, we regard such solutions as unphysical. So they're saying that basically the case where k is not equal to or is not proportional to the metric, that's just not realistic, so we're just not going to worry about it. Right, okay. Oh, we might not make it. I have a meeting in an hour and a half. We'll do our best, though. We'll go as long as we can before we have to call it there. Equations 9 and 14 have the form of a Codazzi equation. So equation 9, remember that's the curl here, and then equation 14 is this guy here. Now, so a Codazzi equation is just a curl. That's what this symbol means. It's just a curl of a two-dimensional array, and you set it equal to 0. And that array should be symmetric, by the way. So C here is termed a Codazzi tensor, following the terminology of 34 and 53. Fine. One can perhaps imagine a class of theories defined by an equation of this form. Now, there is some debate over whether equations of this type are predictive. In particular, it has been claimed in 16 that the Codazzi equations are underdetermined, and in a responding comment, it was claimed that this only occurs for highly symmetric spacetimes. In the following, we attempt to shed some light on this dispute. I am dad to kids. This is currently live streaming on YouTube just as well as on TikTok. So go enjoy, watch over there, subscribe. If you're watching on TikTok and you're worried about where these are going to go, if you're worried about where I'm going to go subscribe on YouTube. Same name there as it is here. And the audio is better. Anyway, so they're going to try to shed some light on this dispute. Contracting equation 18, one obtains this. So what they're going to do is they're going to take equation 18 and they're going to trace between A and C. So this is now a three-dimensional array. They're going to add up along the first and third diagonal. They're going to add up on the diagonal of the first and third entries. So they're going to do 1, 2, 1 plus 2, 2, or sorry, 1, 2, 1 plus 2, 2, 2 plus 3, 2, 3 plus 4, 2, 4, 2, 4, and so on and so forth. So you'll end up with something that is just a one-dimensional array. And so when you do that, the equation looks like this. You have that this particular combination equals 0. And here C is the trace. It's again just the sum along the diagonals of this two-dimensional matrix. Taking the divergence of equation 18, so now instead of adding up along the diagonals here, they're going to differentiate it again. So you take the divergence, one obtains a wave-like equation. So now you get a different equation. So basically they're starting with some sort of thing called the Codazzi equation, and they're doing stuff to it to see what it implies. So if you contract, if you take the trace, you get this equation. If you take the derivative, you get this equation. When you do that, you pick up some curvature because differentiating a derivative gives you some curvature. That's what's happening here. And then again, you can take the trace of this equation and you wind up here. So this is this box that basically means it's the Laplacian. You probably learned about it in vector calculus. It's roughly d by dx squared plus d by dy squared plus d by dz squared minus d by dt squared, depending on your preferred signature. So they say, of course, equation 20 is underdetermined due to this term. So this term makes it underdetermined. Presumably, they're going to explain that. In an orthonormal basis, that's just like x, y, z, t. The derivative, this is two time derivatives of CTB, disappears from equation 20. Okay. So if you set a to t, and if you set a to t, then the term that has two time derivatives of the t component of c are just gone. They just don't show up. So the time evolution of those particular parts of the arrays, the first component, the t component, it's ill-defined. We just don't know how those change. The equations are indeed underdetermined. That's what it means. It means that you have some equation that doesn't tell you what happens to something. However, equation 20 reveals a straightforward resolution. One should supply the Codazzi equation with a constraint equation, and a natural one is the divergence-free condition. So this is just taking the divergence, again, in the vector calculus sense, which is essentially a statement that C satisfies a local conservation law. This is natural in the sense that each term in equation 15 for CAB independently satisfies a conservation law when the Einstein equation holds up to a cosmological constant term, and in particular when the energy momentum tensor satisfies local conservation. That's fine. I didn't get the equation 20 part. So roughly what they're saying in equation 20, so this is a consequence of the Codazzi equation, but if you tried to solve this, you would find that at least if you tried to solve it for C, because C is the unknown here, if you tried to solve it for C, the equation wouldn't give you enough information to solve for it. In particular, there isn't anything that tells you about how the part of C in the t direction, so replace one of these indices with t, it doesn't tell you how that changes with time. And that means that you just can't determine the entirety of C. It's underdetermined. Of course, an attempt to directly solve the Codazzi equations, supplemented with the constraint, may still lead to ambiguities, but such ambiguities correspond to a partial freedom, which we restrict in the next paragraph, in choosing initial data for CAB and DT-CAB for the system. So instead, they're going to consider this system, rather than the original one. Essentially, they're just throwing away this term and replacing, or they're just demanding that this middle term here, that's 0. And so that's what they're saying here. And if that's 0, then you're just left with everything except this middle term. And so they're looking for solutions to equation 18. Equation 18, remember, is the Codazzi equation. So, while solutions of equation 18 satisfying the divergence-free constraint will also satisfy the system in equation 22, there's no guarantee that solutions of equation 22 will satisfy equation 18. So, what's being said here is that in order to get to equation 22, we had to take the derivative of equation 18. So if you take the derivative of something and set it to 0, you're losing information. So, for example, let's say I have the equation x equals 5, right? So that's an equation that has exactly one solution, x equals 5. But if I take the derivative of that equation, then I get, let's say I have an equation like x equals y, or something like that. Let's say that the equation is y equals x, right? That's a solution. It tells us what y is in terms of x. If you take the derivative of that, you get that the derivative of y is equal to 1. Now, there are a lot of things that have a derivative of y being 1. X plus 1, x plus 5, x minus 37, but none of those are x equals or are y equals x. And so what they're saying is that if you impose a derivative condition rather than the original equation, some of the solutions to your equation might not satisfy the original equation. So that's what they're saying here. They're saying that there is no guarantee that solutions of equation 22 will satisfy equation 18. Although it's always the case that equation 18 will satisfy equation 22. Equation 18 being the Codazzi equation, this guy here. Okay. To identify the conditions on the initial data that allow one to recover solutions of the Codazzi equation, so now they're saying, okay, well, what can we do to make sure that we do always satisfy the Codazzi equation? We consider the application of the D'Alembert, that's what this square is called, it's called the D'Alembert, to the following quantity. So they're going to apply the D'Alembert to the curl of the Codazzi. Now this thing is supposed to be 0, remember. That's the Codazzi here. There's supposed to be 0. But they're going to take, so I mean, if that thing is supposed to be 0, then taking 2 derivatives should also give you 0. So they're going to apply 2 derivatives, the D'Alembert, which after using equation 20, which is this guy again, they're just going to do some fairly straightforward rearranging, and they find that the D'Alembert of Q is this horrible mess of things. Don't worry about what the equation actually says. In principle, we could check and make sure that's correct. It's probably correct. These are fairly straightforward calculations. Note that the right-hand side contains at most first derivatives of C. Now, this is quite unusual. So Q has 1 derivative of C, because there's 1 nabla, and then the box has 2 derivatives. So in principle, there should be 3 derivatives of C built in here. However, after doing the calculation, you find that all but the first derivative cancel out. We only have one derivative of c at most. The right-hand side contains at most first derivatives of c, and also that the divergence-free condition removes the first term. So if you want to impose the divergence-free condition, this term here goes away. One can also then regard equation 24 as a wave equation for q, with c being an independent variable satisfying 20 and the constraint 24. So you demand that c satisfies this equation, and that it also is a constraint in this equation for some q. It's a thing that you can do. I don't know why you would do that, but maybe they'll explain. Now consider initial data consistent with equation 18. So we just want to, so we're imagining that you have a slice of space. Or you have a slice of space-time, also known as a snapshot of time. And we want to ensure that whatever is going on at that time, it satisfies, or at least it's consistent with this equation. Now again, remember, this equation tells you that, in some sense, like a derivative of some kind of curvature thing should be 0. So this means that you can evaluate that on your slice of space-time, and as long as it's consistent, then you should be okay. So that's what we're going to do. We want to consider initial data that's consistent with that equation. And if that initial data is consistent with that equation, then q is also 0, because q is that equation, right? But we don't want the derivative of q to be 0. That's fine. For non-vanishing curvature, the right-hand side will generically produce a source unless c is proportional to the metric on a Cauchy hypersurface, and c is covariantly constant. Now, a Cauchy hypersurface is just a slice of spacetime, basically. It's like a snapshot of spacetime, a moment in time. This indicates that if c is not proportional to the metric, and c is not constant, this is bad English. Oh, and c is not constant satisfies equation 24. What's equation 24 again? Yeah, so we want c to satisfy this. We want the derivative of c to, whatever it is, satisfies that equation. On a Cauchy surface, the time evolution of c under equation 20 will in general generate violations of equation 24. So you take c so that it's compatible with equation 18 on your initial time slice, right? And then, if it's true that your original c is not proportional to the metric, and this equation is satisfied, equation 24, on that time slice, then if you then propagate off of that time slice using equation 20, this equation tells you how to, like, what happens next in the next moment of time, then it won't be true that this equation 24 continues to be satisfied, which is a pain. There may also be special cases, highly symmetric spacetimes, for instance, in which equation 18 may admit non-trivial solutions, c not proportional to g, but one cannot expect the existence of solutions to equation 8 for generic initial data. So generally, these are, I guess they're saying that equation 18 are generally not going to have solutions for any initial data. If you give me what's happening at a moment in spacetime, you might not know what's going on. You might not be able to solve the system. Okay, they're going to summarize. Great. To summarize, the Codazzi equation, supplied with the divergence-free constraint, implies that C satisfies equation 22, which has a well-defined initial value problem. Equation 22, again, being this guy. This guy has a well-defined initial value problem. While equation 22 also admits solutions that do not satisfy the Codazzi equation, one restricts the space of initial data to eliminate such solutions that remain. The preceding analysis surrounding 24 indicates that in a general spacetime, one can only guarantee the existence of solutions to the Codazzi equation for initial data also satisfying C equals C being proportional to the metric, and the derivative of C being 0, where lambda is an arbitrary constant. Again, cosmological constant. Other solutions will likely require background geometries with special properties, as argued in 51 and 52. We find that both sets of authors present valid points. That's funny, they're not actually taking a side. Theories based on the Codazzi tensors are indeed underdetermined, but the space of solutions is nonetheless highly restricted in generic settings. Now, I don't have a lot of time left, and we're not even halfway through. So we might... Oh, well, we only have 3 pages left. Do we read the... Let me just quickly scan it and see if it's interesting. Well, we're gonna skip it. We're just gonna skip to the discussion. Let's just read the discussion, then we'll call it there. Because we just don't have enough time, unfortunately. In this article, we considered some theories in which the CC arises as an integration constant and yields the Einstein equation without additional constraints. This class, by the way, if you want to read this on your own, you absolutely can. It's freely available online. Just type in this number, this thing on the left, type that number in, 2406.00932 V4, and it'll just pop up with this. Right. This class includes trace-free Einstein gravity, the Codazzi equation, the and conformal killing gravity. An interesting question which we have not considered is whether there are other theories that satisfy this property. We've made an attempt to consider all the proposals in the literature, but the existence and construction of other theories sharing this property, which may perhaps avoid the properties discussed in the following paragraphs, is an interesting question for future investigation. You know what that means? That means that it was too hard to do that, so they're not going to do it. That's not quite true. It's just sort of true. That's what I mean when I say it's an interesting question for future investigation. I don't want to, look down upon the authors here. They're probably actually looking at it. We revisited a recent debate concerning the issue of non-uniqueness of solutions to equations of Cotton gravity in symmetric reduced settings. That's a typo. By taking additional derivatives of the Codazzi equation, we find that solutions of the Codazzi equations must satisfy at least one of 2 conditions. Either the solutions coincide with that of the Einstein equations with an arbitrary cosmological constant, which is what we want, or that certain contractions of the curvature tensor, the Codazzi tensor, and their derivatives must vanish. In particular, all terms on the right-hand side of equation 24. So this guy, all of these terms have to vanish. Must vanish. The latter can be satisfied in situations of high symmetry, even if the solutions do not satisfy the Einstein equations. But if we regard such non-Einstein solutions as physical, the right-hand side of equation 24 must vanish exactly, even under perturbations. This paper, it came out a few months ago, but this is the most recent version. It came out yesterday. It is unlikely that such conditions can be satisfied unless the perturbations are highly restricted, and one may, in this manner, argue that such non-Einstein solutions are unphysical. We find that the Codazzi equations can in principle be closed with the addition of the divergence-free constraint so that such non-Einstein solutions can be excluded at the level of initial data. Then they go on to talk about the variational principle, which we didn't read, so we're going to skip that. We're going to skip that. Yeah, so there was stuff about ghosts and stuff, which we didn't read. Let's just read the last paragraph. It may be that the approaches we have considered here ultimately trade austerity and completeness, as we do not expect our theories to be fundamental, for the avoidance of the extreme fine-tuning problem arising from vacuum energy contributions to the CC. Some readers may regard this as too high a price to pay. That's very poetic. On the other hand, there is some hope that perhaps one can reorganize the action and integrate out the appropriate degrees of freedom to obtain a more natural form for the action in which some principle or symmetry may be more easily identified. By the way, this statement here is what physicists refer to as beauty in their equations, or naturalness. If we go look at their actions, this is like a horrible equation. And so like they're saying, look, these are not good equations. Maybe somebody can do better, and then it'll look prettier. And then maybe it'll be worth considering. A fair question, which we have not addressed, concerns the mechanisms that set the value for the CC. While a fine-tuning in the early universe can be avoided so long as the field equations remain insensitive to the cosmological term, a mechanism for determining the initial data specifying the CC is needed. Yeah, that's true. You have to specify that. In short, our work shows that the class of approaches we have considered are viable according to some basic criteria, but at the same time, this approach illustrates some of the challenges and trade-offs that one must make in order to avoid these problems. In any case, we hope that our work can provide some guidance for future explanation of scenarios in which the CC arises as an integration constant. I think that's... You can't find the full paper? There will be a button where you can click on PDF on the top right. What you found is you found this. Click on View PDF. It'll take you there. That's what you have to do. So, that's this paper. So this paper, I mean, like, we didn't read the variational principle stuff where they actually have the new results. The part that we read was primarily a review of these different theories of gravity, but I think it's instructive just to see how many different ways the cosmological constant problem can be solved, right? You can just solve it. Yeah, you can just solve the cosmological constant problem without worrying about fine-tuning, as long as you have a different theory of gravity. And it just works, right? So in that case, yeah, maybe the cosmological constant problem isn't a problem, and maybe there's no such thing as fine-tuning. Anyway, so the paper that we were reviewing is Cosmological Constant as an Integration Constant by Justin Feng and Pisin Chen. That's a Pisin Chen, I don't know how to pronounce that. They're both out of Taiwan, which is cool. And yeah, overall, I think it's a very good, at least the sections that we read, I think was a very good review of the different parts of the literature. I think that besides the one typo, I didn't see any particular issues with it. So overall, would rate it at, I'm not going to rate it, but it's a good paper. I like it. I'll probably end up actually reading the rest of it on my own, just to kind of get a vibe for what they're doing. So for everybody who's been watching, this has been the 14th peer review. It will be live on YouTube. It'll be uploaded on YouTube in like 2 minutes. And then you can go watch there if you want. I'm going to end the live here though. I have a meeting in about an hour and I'm going to take a chill pill for a little bit. I'll see you guys tomorrow for Ask a Physicist. Remember, follow me on YouTube. I'm going to be taking questions both on YouTube and on TikTok tomorrow. So if you're watching on YouTube, you can ask questions. If you're watching on TikTok, you can ask questions. But make sure to watch on YouTube. The audio is better there. All right. See you, everybody.